What? Check, check. Come back to me. Hey-o. Microphone's back online. Cool. We're looking at 5.2.5. We've already done 104 and 105 in the live class version. So now it's just me in my room. Let's look at 103 for a hot second. You don't have to do this problem, and I don't think it's a very good AP Calc question, but it's a cool question anyway. So let's take a look at it at the front of this video. The first thing that I don't like about it is absolute value functions aren't super important. We're going to see another example later on in this video of that, but what I do want you to note is that this is going to split up into two separate ideas, and it's going to happen whenever the inside of that function equals 0. And if you go and solve this, I think you also have to recognize that 0.125 is 1/8, and the cube root of negative 1/8 is 1/2. And so the graph is going to look something like this, because if you took the negative part of a cube root function, which looks like that, and flipped it up above, it would look like that graph that you have there. So this is not going to be differentiable, but I did want to take a look at it on Desmos for a hot second too, just to get another idea of what this is. And I understand this video is going to be a little long because I'm doing a problem that you don't need to do, but you know I like to look at these things anyway. So I'm going to go ahead and put myself on, or put Desmos on the top. You can't see my face anymore. Here's our original function, the absolute value of x to the third power plus 1/8, like that. That is the original function, and that you can see the graph of this is splitting up right there. Now if you zoom in on this, you can see pretty clearly that it's not going to be differentiable, and the limits are not the same thing on both sides, which is a typical thing that happens with absolute value functions. We have a different slope on this side and a positive slope on this side, and they're not the same slope on both sides, so the limits don't match up, and that's why the derivative does not exist. So I'm going to go ahead and move this back to the bottom layer of this so you can not see it anymore, and here we're back. So that's a cool question, but it requires a lot of advanced graphing stuff that I don't really think I want to talk about too much today. However, what we do want to talk about is as our derivatives get more complicated, what we're expected to do with them becomes more and more too. So I hope you're not feeling bogged down by this. These are going to take some time. The answers are going to be a little bonkers, but hopefully you're not feeling so unconfident that you don't even pick up a pencil and try it. It's very possible for you. It's within your grasp. You are very intelligent people, and you can absolutely grasp what's going on in these problems here. So let's go ahead and start with problem A, which we got to take the first and second derivative of, because we're looking for the second derivatives of these problems. Now these are going to be a little weird, but let's just go for it. Okay, so the derivative of A. Well, the first thing, before we can find the second derivative, we got to find the first derivative. I did a lot of work for the previous problem off here, so I'm actually going to end up doing a lot of this problem maybe off to the right of this. This is going to be my work for 106. The first problem is problem A, and the original function is the sine of x over x. Now, I certainly don't expect at this stage for you to be free of memorizing the quotient rule. However, the sooner you can start thinking about these things and doing them as you work in your head, the better you'll be off. Personally, I think it's a good idea right now to keep making this little chart there to help you organize what's going on. The derivative of y, the first derivative, dy dx, is going to be the original bottom times the original bottom times the derivative of top, so x times the cosine of x, minus the original top times the derivative of bottom, so just sine of x, and that's all over x squared. That is the first derivative. We saw that as part of our work today, in class today. Now, we're not looking for the first derivative, we're looking for the second derivative, so we're going to repeat this process again. It's going to be a lot more complicated, though, because unfortunately, just the top of this fraction alone is going to require the product rule in its derivative. The derivative of v is relatively simple, but the derivative of u is going to take the product rule with x and cosine x, and not to mention sine of x too. So we got a lot of things to think about here. Let's talk about this derivative, du. Well, when it comes to just that green part there, you got to do the product rule. And that would be the original first thing times the derivative of the second thing. So I'm going to write this as negative x sine of x. That's the original x times the negative sine of x that comes from the derivative of cosine, plus the original cosine times the derivative of 1, or derivative of x, which is 1, so plus cosine x. And then you still have this minus sine x to contend with. Got to take the derivative of that too. That's going to be another minus cosine x. The nice thing there is that these are actually going to cancel out. And so your derivative is actually just negative x sine of x. So we'll use that when it comes to taking our derivative. So when we get crazy, here we go. Second derivative, d squared y dx squared is how we write that. Second derivative. Again, we want the original bottom times the derivative of the top. So we want x squared times negative x sine x. It's going to be negative x to the third sine x minus the original top times the derivative of bottom. So that's going to be 2x times x cosine x minus sine x. And this is all going to be over x to the fourth power, x squared squared. Woof. Now, there's a lot of simplification that we could do here. I noticed that the book's answer is completely simplified, so I'm going to try to work through a few things as much as I can here. The first thing I would do is I would expand out the top, negative x to the third sine of x minus 2x squared cosine x plus 2x sine of x. This is all over x to the fourth. And I like this because what you're going to see here is you're going to see an x cancel out. At least one x is going to cancel out of every one of these terms. And in fact, you're going to be left with some pretty relatively simple things here. You will have, let's see, you'll have a negative 1 over x times the sine of x in that first chunk there. You will have a minus 2 over x squared cosine of x in that middle term. And you'll have a plus, let's see, it would be 2 over x to the third sine of x in that last chunk there. That's probably the simplest I can make that problem. Not so tough, but also kind of rough. So don't be frustrated if you're getting stuck on these things. Next, we have the cosecant squared minus the cotangent squared. For part B, we have y equals the cotangent squared of x minus the cosecant squared of x. Just one more double check, make sure I got that right. Cosecant minus cotangent. Okay, oops, I'm glad I checked it. Cosecant minus cotangent. Cosecant squared of x minus cotangent squared of x. You know, I don't like this problem too much for you guys because what you might be tempted to do is run these both through the chain rule with the derivatives that you know. And I feel like this problem would be better done if we knew a few things about the cosecant squared and the cotangent squared of x first. But you know what? Since you guys just learned the chain rule and you learned these derivatives, I think it might be actually pretty reasonable if we ran this through our basic derivative understanding. Although I'm pretty sure that these cancel out in some way. Let me think about this for a minute here. Let's see. I'm going to think about the one trig derivative that you should memorize. Sine squared plus cosine squared of x equals 1. This means that if we divide, let's see. If I were to divide, if I wanted a secant here, or a cosecant, sorry, stand by. You know what? Let's just go for it. Let's see what happens. dy dx. Let's use our new derivatives that we learned today, and we'll chain rule them together. These are all something squared. So the derivative here would be 2 times the cosecant of x to the first power times the derivative of the cosecant, which is negative cosecant of x, cotangent of x. I can say it? Yes. Oh, yeah. No, Stacey already talked to me.
Okay. Good.
I'll be there. I'm going to finish this, then I'll be there.
All right.
Yep. Minus 2 times the cotangent of x times the derivative of cotangent, which is the negative cosecant squared of x. Wow. Now that I think about this, I really don't want to do this as a second derivative, so I got to think for a second here. Let me quickly Google, let's see, Trig Identities. I'm sure that I know some things that I can do. I guess maybe what we're doing by doing it this way is illustrating this is not the best way to handle it. Looking for basic ones that involve this. Ah, yes, I knew it. Oh, yeah, okay. Let's not do this. I'm going to leave it here as a memory of a way that we should not do this problem. I mean, that's not wrong, but I don't want to do that this way. Let's think about our sine squared plus cosine squared x equals 1 thing. If you divide everything in this problem by the sine squared of x, what you get is 1 plus the cotangent squared of x equals the cosecant squared of x, which is cool, if you really think about that. Now, what that means is that we can probably simplify quite a bit out of this thing. Like, for example, I know that the cosecant squared of x is equal to 1 plus the cotangent squared of x. Oh, and look at that. That's awfully nice. Let's not do this. It's going to make this problem much simpler. Because what that means about our original function is it's 1 plus the cotangent squared of x minus the cotangent squared of x. These two cancel out, and then y is just actually equal to 1, which means your dy dx is equal to 0, which means your second derivative, your dy squared over dx squared, is also equal to 0. And I like that answer a whole lot better than doing multiple product rules inside of this thing. You don't want to do that. Trig identities, I mean, I don't know how fair that is for the AP test, honestly, but we'll keep going anyway. Question C is going to ask us what the derivative of square root of 1 over x is, or second derivative, rather. Like that. This is, again, a chain rule. I think I would prefer to think about this as the square root of x to the negative 1 power. Actually, I'll do you one better. A much better way to do this problem would be to think about it as x to the negative first power to the 1/2 power, because now it's just x to the negative 1/2 power. And now we can just use the power rule, and we can skip everything else we know. No chain rule necessary, no product, no quotient, just use plain old power rule. Your derivative, your first derivative, dy dx, will be negative 1/2 x to the negative 3/2 power. And you could clean that up if you want to, but since we're not going to land at this destination, it's going to look something like that. We have to take the derivative of this, so we're just going to do that. Same pattern again. D second y over dy, dx squared. Let's see, if we do the power rule with this guy here, we're going to have a positive 3/4 x to the negative 5/2 power. And, you know, again, we could simplify that, but why would we? Let's just leave it alone. That's the answer. And question D is a dumb question. Again, I do not like absolute values when it comes to calc, but I think it's worth remembering what's going on here. The derivative of absolute value of x minus 2. What you have to think about here. This derivative does not really exist since it's not differentiable at 2. At x equals 2, there is a sharp, nasty corner on this graph, so it's not differentiable at 2. Now, what you could do if you wanted to be super advanced about this problem, you could make it a piecewise function, where it's negative x for x values that are less than or equal to positive 2, and it could be positive x for x values that are greater than 2. You could do that. Now, what's cool about that is that you can actually take the derivative of this, the dy dx, which is negative 1 for x values that are less than or equal to 2, and it's positive 1 for x values that are greater than 2. And if you take the second derivative, both of those have a second derivative of 0. And now it doesn't actually matter if you're less than or equal to 2 or greater than or equal to 2. The second derivative is 0. It's kind of like asking what the concavity of this graph is. There is no concavity. They're all straight lines. So the second derivative is 0. And that's actually an answer that you can get. I don't like that problem a lot. I feel like it's kind of tricky, and you would never be asked anything like that on the AP test, but it's a cool question anyway, and it's worth thinking about for a hot second. Let's move on to 107, where we got some integral problems here. Once again, we're going to use whatever the best strategy is, and once again, you're going to have to wait while I find the problem again, because I zipped all the way back up to the chain rule, because I was zooming in and zooming out too aggressively. I did notice really quick that the first question is going to require straight-up geometry. We're looking for the integral from 2 to 3 of that thing. What happened again? You'd be kidding me here. Okay, I'm right here. I'm not going to move again. I'm right here. Okay, the best way to solve this problem by far is to use geometry, because just like we saw in the previous problem, the absolute value equations are going to be made out of straight lines. We can easily find the area of these chunks. So we're going to be very careful about graphing this, though. First of all, it's the integral from -3 to 2. And it's an absolute value. It's an absolute value that's been moved, let's see, up 2 and left 1. And also turned upside down. I don't know if you can see I don't want to zoom in too aggressively. This is the graph has been moved left 2 spaces and up 2 spaces, and it's been flipped upside down. So we're going to graph that. I'm going to start by finding the vertex at -1, 2, right there. And this graph, instead of coming down and then bouncing back up, is actually going to go up and then come back down. Conveniently, it's going to cross at -3 and 1. It's going to create a little bit of negative space in our thing here. So now, this breaks this problem down. If you graph it carefully, really breaks this problem into all you got to do is find the area of 2 triangles. This triangle here has an area of 1/2 times its base, which is 1, 2, 3, 4, and its height, which is 1, 2, and that's just going to equal 4. This negative triangle here has an area that is 1/2 times 1 times 1, which is 1/2. We just need to remember that's a -1/2 because it's below the axis. So the final answer for the area between the curve and the x-axis is 4 minus 1/2, or 3.5 and 3 1/2. That's the answer. Problem B is an indefinite integral, and therefore we're just going to get a formula. It might be a good idea to think about this differently before we start. I notice we have 2t to the -2nd power minus t to the 3rd power in there. So now we just got to think about antiderivatives. The antiderivative of t to the -2nd power is t to the -1st power. Got to go up 1 degree. The coefficient there will need to be -2 so that it cancels out. That will take care of that. The antiderivative of t to the 3rd is t to the 4th. And we're going to need to put this over 4, so that will cancel out when we bring the 4 down, plus c. That's the answer there. Question C is also, don't even worry about question C. It's equal to 1. Simple. Oh, sorry, 0. I was brain dead for a minute there. 0, because an integral that goes from a number to itself doesn't have any area at all, so there is nothing to worry about there. And question D, your first trigonometric inverse trigonometric integral, where you got to go back in time. Again, it's the same question, the antiderivative. What function has a derivative of secant squared? Turns out that is the tangent of x plus c. A very common question on AP Calc tests is a question like that, question D. See, you guys are going to do fine on the AP test because a lot of the stuff we do in class is more challenging than what you'll see there. You just have to do it all at once, which is what you practice when you do these assignments. 5108, put the following function values in order from least to greatest given the graph of f of x to the right. This is a really good question. Again, you see these on AP tests a lot too. You're never really going to know usually what these things are. I can tell you right now that f of 2 is 0. Just from looking at the point 20 is on this graph. Now, f prime of 2, I'm not going to be able to tell you what it is, but I can at least tell you that it's going to be a negative number since this graph is decreasing. The slope of the tangent line there is decreasing. It's negative something. I'm going to say -1 just as a placeholder. But all you got to know is that it's a negative number. So you already know that if you're arranging these in order from least to greatest, you already know that f prime is before f of 2. F double prime of 2 is going to be a positive number, and the reason why I know that is because this graph is concave up. So f double prime of x is going to be greater than 0, or positive. I have no idea what it is, I just know that it's positive. And so the order goes like this. F prime of 2, which is negative, followed by f of 2, which is 0, followed by f double prime of 2, which is positive. That's the least to greatest order of that situation. Just requires you to think about that. We're not going to worry about question 5109 right now. It's definitely a question we will deal with in the future, but right now at this moment in time, I'm not super worried about it. So there is your long weekend homework. Thank you guys. I just can't express enough. I don't know if I say it enough in person in class or if you even make it to the end of these videos. I'm just so proud of where you've come, and I just want you to keep it up and do the best you can for the remainder of the year. I know it's your senior year. I know things are close to the end. Just keep pushing. You're going to do great. I'll see you in the next video.